So today I'm going to discuss about biochemical oxygen demand test or BOD test. The idea of BOD test is understanding how bacteria or living organisms in the water can consume oxygen in order to, of course, consume organic matter or any other matter that is going to demand oxygen. When the bacteria eat that, they are going to demand oxygen. So we are going to determine how much is there and how fast they are responding. So the quantity, I'm looking at quantity and rate. Now in order to do that, what we do is we have to have a bottle where we can measure the dissolved oxygen, and we put in water maybe containing bacteria, that can eat this particular type of waste. Then we aerate to aerating. So you have water here with your oxygen. We aerate. Now you can imagine after aeration we have saturated dissolved oxygen. So the dissolved oxygen now is a saturated dissolved oxygen, or in other words, for this particular test, this is DO initial. That's the initial DO. Now you are throwing in your waste. And waste means it can be organic matter or any organic matter, for example glucose, you can throw in. Then what we do, we close the lid. Aerate means, I think aerate means actually it's mixing, which I didn't tell. So we close the lid now with a dissolved oxygen probe going inside this one, and then we measure the DO meter. So we measure the DO from here. When you measure the DO from there, what will happen is, you can imagine as the bacteria eat the organic matter, they consume oxygen. So organic matter, and then they consume oxygen. It's done by the bacteria, and they give out carbon dioxide and water. So if they consume oxygen, that means they are consuming organic matter. If they consume organic matter, that means they are consuming oxygen. So both goes hand in hand. It doesn't happen, one doesn't happen without the other. Okay, now if you now try to look at the profile of the oxygen, how the oxygen is going. Now I'm going to plot the oxygen. You have almost saturated level of oxygen, which I am calling for this particular test as DO initial. And then this DO actually will go down gradually, because as the bacteria eat and eat and eat, this one will go down, and then this can go down, 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 down. After some time it won't go down anymore, maybe mainly because organic matter is finished. Or sometimes it will happen, what will happen is, if the organic matter is in too much, then oxygen will remain will finish quickly, which I am not looking at it now. So don't worry about this particular curve. Now if you imagine this particular curve, then if you keep on measuring DO and plot it, and then that's the curve you get. So this is the maximum oxygen demand this is the maximum oxygen or biochemical oxygen demand by the bacteria, the maximum biochemical oxygen demand. And then this particular amount is the maximum biochemical oxygen demand. Right? That's the maximum level oxygen can be consumed. This one we call ultimate BOD. Or in other words, we represent this one by L0. If you go and look at any days, for example, after 3 days, you look at the amount of oxygen that is consumed, the amount of oxygen that is remaining. If you look at the amount of oxygen that is consumed, that is the biochemical oxygen demand in 3 days. The oxygen demand that has already occurred in 3 days time. Now if I represent this one as L3, that means the amount of oxygen that is still not consumed, but it can be consumed, so it's remaining. The oxygen demand that is remaining is L3 here. Now similarly, I can write for any time t the BOD days. I can write BOD T is the oxygen biochemical oxygen demand in T days. LT BOD remaining, oxygen demand remaining to be consumed, after T days. Now if that is the case, we can write L is any one that is remaining, L at any time, or LT, doesn't matter. For the purpose of mathematical configuration, you can imagine here, if there is lots of food, the bacteria takes out oxygen very fast. If there is less food, if there is no food left, the oxygen, they don't take away oxygen at all. The oxygen take away is 0. So what you see here is the slope, which is mathematically it is dl by dt, differentiation of this particular curve is proportional to the food remaining at any time. So in other words, I can write an equation, and then that is always a negative slope. If you look at here, it is a negative slope. It's not a positive slope. Positive slope is like this. The negative slope is here. So it is a negative slope. So therefore, I'm going to write dl by dt is minus KL. For this one, if you try to apply the equation, the boundary condition, and then integrate this particular equation, for example, you separate the variables, then you will have this relationship. Then you integrate, t goes from 0 to time t, and L goes from L0, at the beginning was L0, you have maximum dissolved oxygen demand, organic, the L0 is the one that is the maximum at this point, and then it becoming L3 or LT or any time. So L0 goes to LT. Then you will see a relationship, LT will be equal to exponential L0 times exponential minus KT. So what this one tells you, at any given time, LT or the remaining oxygen demand is equal to initial oxygen demand times exponential minus K is a constant value for one type of base and one type of bacteria. or one type of condition times T. This test is usually done at 20 degrees C. We don't do it in any other temperature. Always we do it at one constant temperature, then we adjust according to the temperature. Later I will talk about that one in the lecture, but we do that at 20 degrees C mostly. Now what you see here, so therefore BOD T at any time, BOD T is given by, BOD T is, you can see here, for example, this part BOD 3 is same as L0. This is L0, take away L3. So this is L0, take away L3. Sorry, I always write. So L0 minus L3. Similarly, BOD T at any time is given by L0 minus LT. I hope you understand this particular test and equation that it is going with this one. Now can you please think, before you come to the lecture, think, if I throw in the same waste and then put some toxic material inside, what will happen to this curve? Now if I do other way around, instead of doing 20 degrees C, if I do it at 10 degrees C, what will happen to this curve? It will always follow one important point. Always bacterial consumption of oxygen is proportional to the remaining oxygen demand, or the remaining food. Remaining oxygen demand in this case is food. You had lots of food here at the beginning, which is L0. Then this L0 is becoming less and less, and then when the food remains is going to be 0, then bacteria doesn't have anything to eat, therefore their metabolism or the eating goes down and down and down, so their rate goes down. So that rate is always proportional to the amount of food remaining in the water. Only difference is if you give different temperature or different food or different toxicity, then they have to adjust to that particular situation, but they are proportional. Always this equation is holding. Only the K value will be changing. How the K value will be changing is the one that you have to think about. So I hope you understand this lecture, and in the lecture I will talk more in detail of applications.